Good afternoon. Assalamualaikum. And now we are going to go into the next topic on the feedforward control. See what is feedforward control? Basically, feedforward control is a system which measures the disturbance directly and anticipate effects on the outputs, and it takes the control action to eliminate the impacts of the disturbance on the process output. Before it touches the process output, it is already basically taking care of it. So it measures the disturbance, goes to the controller, and come out with a manipulated variable that is taking care of the disturbance, basically rejecting the disturbance before it comes to, it affects the control output. Okay, so feedforward acts beforehand in an anticipatory manner. While the feedback that we've studied before, there's a disturbance, it will measure disturbance, goes to controller and act on the manipulated variable. But the effect of the disturbance has already been felt by the system, and it has to measure it and then only take effect. So this is a different effect. Acts after the effect in a compensatory manner, and this is in an anticipatory manner. So there's an advantage in using feedforward control, and that's why it comes also under advanced, classical advanced control, because it's not the same format as the feedforward feedback. Slightly different, but very closely similar, and still will become under as an advanced, but based on the definition, but a classical sort of. So there are many types of feedforward being used. For example, in this heat exchanger, to keep the exit temperature by manipulating the steam pressure. So basically, it involves is manipulating the steam pressure to control the temperature. So basically, it measures the liquid flow rate and the liquid inlet temperature of the disturbances, goes into the feedforward controller, acts on the steam control system, so that before it affects the temperature output, it's already taken care of partly by the steam control system. Another one for drum boiler, to keep the level in the drum constant. Again, it measures the steam flow from the boiler, okay, and also flow of the fluid water. These are disturbances where it's acted on by the feedforward controller to control the feedforward input into the drum boiler. Another one is the decision column. Disturbances from the feed flow rate compensation is measured, taken care of feedforward, and then act on the reboiler control or the reflux control. Or the CSTR system to maintain the constant temperature and composition. It takes care of the inlet concentration changes, inlet temperature changes, acts on the control of the coolant or control of the output if necessary. Yeah, it can be either one. But anyway, it's taking care of the disturbance, measuring the disturbance and taking care of it before it really affects the whole system. These are examples of feedforward controller used in chemical process. Basically, let's see the design of feedforward controller using this example. Tank heater, and these are the temperature input coming in, output coming in, and this terms we control the steam coming into the heater to manipulate the temperature output. Okay, so first of all, designing, we develop what we call the feedforward controller, steady state feedforward controller. So first of all, we have to come up with the model of the system. Okay, temperature rise, okay, heat coming in, heat coming out, and the heat to the heater, or can be the steam or just a heater coming in. And so we take since it's a steady state, so we assume there's no change of temperature. We take the steady state equation and design the T. So in order to keep T equal to T set point, then the Q, which is the manipulated variable, should be acting in this form. Okay, and so equation T is the design equation for the steady state feedforward controller, and it shows how the Q should be changing when there are disturbances in the system. Okay, which in this case will be the temperature changes. So diagram. This is going to be the block diagram based on the equation just now, where we take the ti and minus this ti, or set point minus ti, okay, times the fi rho cp, and then it becomes the manipulated variable q here. So this is the feedforward mechanism. You just use feedforward control. This is the feedforward mechanism block diagram for the steady state system. For dynamics, then basically to improve the quality of control during the transient response, we use the same equation, but the dynamic equation we don't convert to steady state. Okay, and then we get into the derivation and Laplace transfer function. We get this equation. Now we want to design the Q, which is the manipulated variable, in the form of equation 5. So this is the design equation for dynamic feedforward controller, not the steady state. Slight variation in terms of adding the extra block, okay, on tau s plus 1. So in terms of the same thing, the disturbance measured but minus by the tau s plus 1, okay, times the set point. Then only you multiply the f rho cp, and then this becomes the dynamic feedforward controller for the whole system. Okay, this is pure feedforward controller. So in terms of performance, you see, for load change, we have a load change into the system. Okay, then a dynamic feedforward gives a bit faster response to the steady state static feedforward control for step point change. So design arises directly from the model of the process. You need the model, of course. The better the model, of course, the better the controller, because it depends on the model. And the design model, the model equations are the tau s plus 1 is fine, and you get a good controller. And the dynamic feedforward is better for set point, also for disturbance changes in most cases, not generally everywhere, but most cases. Okay, so these are the general block diagram for feedforward controller we've seen just now. Okay, and this is the disturbance we measured, taken care by it's minus from the set point times what we call 1 over GD. This is called the set point element, multiplied the equation GD over GP, which is called the feedforward controller element, and the whole thing is called the feedforward control mechanism. This is the process itself. So this is the standard feedforward control. But normally when you have measurement, you need a measuring device. So you have another block for measuring device. Okay, and when you have a control, you need the final control element. So you have a final control element added on, which is the real one, practical one. Okay, so we added these two. So the slight modification, when you add that, this GSP will become GM over the GD, taking care of the GD here, taking GD and the GM coming from the measurement GM, and then the feedforward element is the GD over GP, GF, GM. Okay, slight modification, and then also we have the extra GF final control element inside the loop being taken care here. But this is the feedforward control. The slight difference in additional of the GM and GP block of transfer functions when you talk about in general, when you have feed element of the measurement feed element and the GB, the measurement feed element, the final control element. We put in terms of equation again, the process output will be the GP times the M manipulated plus the GD times the disturbance. Okay, and if we say what set point is a requirement, so we design the M, which is the manipulated variable in its form. Okay, and this is the standard general form, and then from here we can see that the GD over GP is called the transfer function of the main feedforward controller, and the GS 1 over GD is called the set point element. This is the set point element. This is a general equation for feedforward transfer transfer function. Okay, and from 9 and 10 it's clear that the feedforward control cannot be a conventional. There's no PPID equation there, so it's not conventional. And also it shows that the feedforward depends heavily on the knowledge of the process, because it depends on the model for all of the system, GP, GF, GS, GP, GC, GF, and so on. Consider the more general filter, which include, if you include the measuring sensor and final containment as we said before, then we have a more extensive equation. For the design of GC engine can be affected by the following two requirements. So how do we design the GC and GSP? The design of GC and GSP is identified here. For we need this to become zero. We have a ideal feedforward transformation. The GD minus this part has to be zero in the equation before, as we've seen. Yeah, the equation that we see on equation for disturbance rejection. Yeah, we see that it has to be 0. So which means the GC is GD over GF or GM. For disturbance, it has to be 0. It cuts out the second part of the equation in the previous slide. And for set point tracking, this one has to be 1. It has to be 1. Okay, so that you get follows the set point. And for this to be 1, then you get the GSP equals to GM over GD. Okay, looking back at the equations in the last slide, this is what it's supposed to be. And in the real world, okay, when we want to design this dynamic or steady state feed forward, for the steady state one, normally we take the GP to be the gain, process gain, and GD to be the process gain of the disturbance. So when we get so in the GC equation, we just matter using the gain, and the GSP just the gain. And the C and the GC and GSP can be constructed easily in the same way as a proportional quantum with solving problem. So this one can be designed easily if you have a real hardware feedforward control. Of course, you can design this in the software, but before it was in hardware system, so you can just design in terms of gain, which is easier than to design in terms of transfer function. For the dynamic feedforward, the same thing. We approximate the GD over GP by a sort of first order relay system, first order lags, in terms of 1 over alpha s plus 1, and this one is 1 over beta s plus 1. The final equation is in this form: beta s plus 1 over alpha s plus 1. And for the GSP, the same thing. This one is converted into the 1 over alpha s plus 1. So the GSP is just alpha s plus 1. So basically, the controller given by electricity is called a lag lead. This is the lag, this is the lead element, because beta s plus 1 introduce phase lead, the top part, and 1 over alpha s1 adds the phase lag. So we call lag lead controller element. This is how it goes. Okay, so it's just a matter of adjusting these two constants here, and for this one, this constant here, alpha. So the lag lead element is the most commonly used dynamic feedforward control in the real world, practical world. Easy to tune. You get only 2 parameters to tune, and easy to build up a hardware controller by this. And the 2 adjustable parameters are just the beta and the alpha. So this is alpha. No, it's alpha. Okay, and the lag lead can be bought easily and not expensive, and special purpose analog computation device can be designed for this controller. And finally, in terms of advantage of feedforward and feedback controller, we've seen before the in terms of the feedforward controller. Okay, the advantage acts before the effect of disturbance has been felt. This is the most important advantage. It's good for slow systems or with significant dead time. Does not introduce instability, because there's no feedback. Does not introduce instability. However, it requires identification of all possible disturbances and the direct measure. We need to know all the parameters, of course, to be able to implement the model parameters. Of course, it has to measure the disturbance. So if you cannot measure, you cannot cope. It's sensitive to the process parameters, of course, because it depends on the model-based system. And requires good knowledge of the process model. That makes the feedforward controller good. So if you have the better process model, you have a better feedforward controller. For feedback, advantage does not require identification and measurement of disturbance for feedback. It's insensitive to modeling errors. You don't need to know the modeling errors in detail for feedback. And neither is it sensitive to parameter changes, because you're just measuring the feedback and then compare error and then effect and then implementing the PID. But this is disadvantage. It waits until the effect of disturbance has been felt before control action is taken. So he has to measure the Y, and the Y, the disturbance already affected Y, only it can take action. It's unsatisfactory for flow process or significant dead time. Yeah, we can see from the block. So and create instability, because you have the closed loop And then you get the transfer characteristic equation, the transfer function of the characteristic equation, and you see the roots of the equation right or left and so on, as we studied in the precise control. Definitely can be unstable in some cases if you don't design it properly for the feedback part. Okay, so disadvantage and disadvantage, and then you can combine, make the best of both worlds. Okay, combination of the feed-forward feedback will be maintain the superior performance of feed-forward and the insensitivity of the feedback to uncertainties and accuracies. So the best of world, we have still the same thing for the feed-forward and also the feedback loop that we have seen before. So you can combine both of them. This one taking care of the disturbances in particular, and this one taking care of the normal set point changes and being less insensitive to the modeling errors and so on. So it takes care of both worlds. Okay, of course there is some instability involved because it's still a feedback, but hopefully if you design it properly, it should be able to handle instabilities if you have a feed-forward feedback. And in this case, you'll have the normal equation for this one, y equals gmd and so on, and you can define the variable using for both part, the feed-forward part and the feedback part, and the feed-forward part and the feedback part, and then you can design the c over d in this form. And if y equals to set point 0, which means in terms of no set point change, and this disturbance is there, then this one has to be 0. Okay, to fulfill the no disturbance case. Okay, it is 0. So therefore the transfer function is given by this, very similar to the previous ones. Yeah, it's a negative there, gd over gp gf and gm2. And that's all for the feed-forward slide. Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.